Well, welcome back to our course on system engineering. In this lecture and in this chapter, we're going to be talking about model-based systems engineering. And so we'll give an introduction to what that is, and then we'll show some sample products that you can be producing with using this kind of a mindset and the tools that are available. So for model-based system engineering introduction, or MBSE, is a emergency new paradigm for improving the efficiency and effectiveness of system engineering through the pervasive use of integrated descriptive representations of the system to capture knowledge about the system for the benefit of the stakeholders. And that's a quote from Nagoshi from 2016, and you can go ahead and look that up in the textbook if you want to get more details about that reference. As MBSE becomes the typical way of executing system engineering, engineers will be increasingly expected to develop proficiency in system modeling tools, languages, and methods. MBSE does not replace sound system engineering principles. It increases their impact through by its inherent rigor, consistency, and fidelity. With the advent of formal modeling languages such as a unified modeling language, UML, and the systems modeling language, SysML, and using architectural frameworks such as the unified architectural framework, which we mentioned, which is getting to be the standard more than the Department of Defense architectural framework, DODAF, and the Open Group Architectural Framework, TOGAF. The ability of the system engineers to create high fidelity representation of system requirements, behavior, and structures has never been greater. The exploration and definition of system concepts have now been formalized, and a subset of system engineering systems architecting has risen to greater significance. In broad terms, a system architecture can be thought of as a descriptive model of the system or the system concept. After the first formal version of UML was released, the Open Management Group, OMG, provided the first version of the model-driven architecture, MDA. This architecture recognized the shift from a code-centric software development paradigm to an object-centric paradigm, enabled by the then de facto standard for software engineering model languages, UML. The MDA presented a set of standard principles, concepts, and model definitions that allowed for consistency in defining object models across the software community. The MDA delineated between the quote, real system and its representation by a set of models. These models in turn conform to the meta model definition, which would in turn conform to a meta model definition. Several concepts, processes, and techniques were presented in the literature using this concept, although the names differed: model-driven development, model-driven system design, and model-driven engineering. They all were based on focusing on a model and its meta-model to represent the system from the early stages of development through deployment and operation. With attempts to merge software and system engineering processes and principles underway, model-driven development was applied to system development in various forms. In 2001, INCOSE, the International Council of System Engineering, established a model-driven systems design working group to customize UML for system engineering. By 2006, INCOSE and the OMG adopted OMG SysML. And we'll have some separate lectures that will get into the specifics of SysML modeling, but we'll get some overview as we talk about material in this chapter and in this lecture. So let's talk about MBSE, its motivation and impacts. There's a lot of material here, but I'll try and give an overview of it. So first of all, for the need for MBSE, modern system engineering has become increasingly complicated and complex, with emergent behaviors driven by the interactions of hardware, electronics, software, and users. System designs are often developed across multiple organizations who need to collaborate and easily exchange data. The traditional document-intensive systems engineering, DISE, approach depend upon the readers of disconnected documents to mentally integrate them. They also rely on inherently human readable text to convey intent instead of purpose-built language with crisp semantics. What distinguishes MBSE from traditional implementations of system engineering is the process of progressively developing the requirements baseline. Functional architecture, physical architecture is structured around the incremental refinement of the integrated set of increasingly detailed descriptive models. These models become the principal means of knowledge capture and communication about a system over its lifetime, replacing the large number of discrete documents that become inconsistent as each independently evolves over time. That's once again is going back to Nagoshi there with that quote. In 2018, the United States Department of Defense released its digital engineering strategy. This strategy is intended to reform defense acquisition to allow military systems to be released at the speed of relevance. The traditional waterfall approach to create thousands of requirements in the years-long development cycle may soon give way to the MBSE-supported concept to preliminary design review, PDR. The digital engineering strategy has 5 goals. Formalize the development, integration, and use of models to inform enterprise and program decision makers. Provide an enduring authoritative source of truth, incorporate technological innovation to improve the engineering practice, establish a supporting infrastructure and environment to perform activities, collaborate and communicate across stakeholders, and transform the culture and workforce to adopt and support digital engineering across the life cycle. In terms of MBSE use in the system engineering lifecycle, MBSE adds value wherever it is used within a lifecycle. Errors and inconsistencies between disconnected source documents and artifacts can be readily identified as the model is constructed and matured. The greatest value is typically gained when MBSE is applied from project inception. This allows all relevant data to be modeled as they are created, rather than reformatting and refactoring later. It also permits the development team to see early value as inconsistencies are identified in the inherent rigor of the modeling effort, structure, and team's efforts. The lead systems engineer has an added responsibility to define where modeling fits into the project, development plans, and architecture. By having the model as a resource throughout the development plans and architecture, by having the model as resources throughout the development journey, teams gain a sense of ownership rather than a feeling that an external framework is being imposed on their work. In MBSE, if MBSE is implemented later in the life cycle, there are diminishing returns for the effort. However, just as converting engineering drawings to CAD can provide benefit for the sustainment and maintenance of legacy systems, a late-stage MBSE effort can also add significant value in reverse engineering or upgrading a legacy system to extend its life. Note, we'll have a couple of MBSE-based diagrams that will be looking at the Apollo mission, so we'll see an example of that. Ancillary tools for analysis and management facilitate the unification of the descriptive system model and product line engineering, PLE, product lifestyle management, PLM, and product data management, PDM, to provide the ability to share as conceived, as designed, as built, as maintained, and as disposed information about a system. This has significant implications for improving long-term maintenance and logistics support of consumer goods, such as automobiles, in addition to aerospace, health, network, and defense systems. Next, let's talk about differences between MBSE and traditional document-intensive system engineering. The basic notion behind MBSE is that a model of the system is developed early in the process and grows organically over the system development life cycle until the model becomes the built-to baseline. Early in the life cycle, the models have low level of fidelity and are used primarily for decision-making. As the system is developed, the level of fidelity increases until the models fully represent the architecture. Architecting defines what to design, while design defines what to build. And so that's another quote that we have in our textbook. Although the approach may appear similar to traditional system engineering approach, several significant differences exist between the two. The foremost difference is the products created by each approach. In traditional system engineering, including either of a structured analysis or object-oriented approach, the primary products early in the system development lifecycle are static representation of the system in a hard copy or soft copy format. In MBSE, the primary products are models, integrated collection of information, elements, attributes, and relationships, which can be queried, displayed, error-checked, and executed. Reviewing a model-driven system design at any point in the lifecycle involves interrogating a set of models or reviewing an automatically generated set of derived work products, such as tables, matrices, or diagrams. Additional process improvements are also possible because the traditional text-based requirements was formerly the primary method of communicating the design intent. Large numbers of requirements were created. This directly contributed to administrative challenges, change control, and wordsmithing of requirements that did not directly add intellectual content to the development effort. The number of text-based requirements may be reduced if stakeholders are able to consume model content directly. This inherently reduces the source drain associated with stewarding the requirements, such as there is no reason to translate a circuit diagram or construction blueprint into a text stated how to wire a resistor or where to place a window. Property-based descriptions of well-formed model elements, such as a state machine, can clearly communicate design intent and engineering direction. A relatively small set of user needs, goals, measures of effectiveness, and key performance parameters can be used to shape the system model. Detailed authoring of systems, subsystem, and component requirements can be deferred until the relevant portion of the model are suitably mature. This defers and reduces the significant overhead of requirements management and permits the system model to be used to rapidly facilitate analysis and communication of intent between stakeholders. In addition, automated comparison of value-based requirements with analysis results can immediately highlight shortfalls and deviations. Requirements that simply duplicate model content in textual form could be eliminated if stakeholders accept and understand the equivalent model representation in products. Because SysML models are essentially graph databases of elements, attributes, and relationships, they are machine readable and can be used to drive analysis and may be subject to automated analysis. For example, the use of validation tools can error check models either automatically or on demand. By incorporating rules based on desired modeling conventions, say an organization's style guide, these validation tools can provide immediate feedback to modelers about errors and gaps. Some errors can be eliminated completely by careful customization of the model language. For example, power usage relationships may be created to connect power scenarios and part properties that are consuming power during a given scenario. By customizing the language so that only legal sources of power usage relationship is a power scenario, and the only legal target is a part property. A modeler effectively prohibits the creation of illegal relationships. In addition, on-demand queries can be created to answer key program or system engineering questions and enable stakeholders to gain insight about the system being modeled. In terms of modeling and excellence. The creation of an authoritative system model provides opportunities to improve the development process. A competently executed model should represent a given element of information once and reference it throughout the rest of the model as needed. The elimination of redundancy avoids potential conflict and improves efficiency. So the textbook refers to a source that discusses elegance in modeling and its applicability to designs. And it is in term typically applied to solutions that are simple but effective. And so Maddie is a reference here. He provides us 12 key metrics for elegance. And so we'll just list those here. Purposivity, which is regarding the accomplishes purpose or goal with minimum side effects / negative consequences and given priorities. Parsimony, which it accomplishes intended purposes with a minimum number of components, resources, and intentions in routine / contingency situations. Transparency, inspectable system behavior during operations or use. Scalability, design scales linearly with an increase in complexity. Sustainability, endure CASA effectively in the face of anticipated and unanticipated change. Bonding, visceral / emotional connection with the system / operations. Efficiency, accomplish desired outcomes with minimum resources, effort, and waste. Evolvability, adapt / extend seamlessly to meet a new market / operational demand. Affordability, total cost within the customer's acceptance threshold. Usability, ease of use with neglectable errors and error rates. Utility / impact, monetary / non-monetary net positive impact achieved for investment made. And predictability, system behavior can be determined in a variety of future contexts and scenarios. So well-formed system models support design elegance. Metrics can be developed for a given model to directly assess its parsimony and efficiency. In addition, behaviors can be broken down, and the interconnectivity of these functions can be analyzed by design structure matrices or other methods, and they can be partitioned using a variety of algorithms. This allows the system model to directly support non-arbitrary segmentation and allocation of the function to individual components. Well, let's talk about something called the elegance equation. And so going to the reference here, Maddie from 2012 work, there's also something from Vinerick in 2018 that propose that every model has several factors that may be used to describe it. So here we have this equation, and so we have the efficiency factors, which is the output over the input, and so we're showing that in a couple elements here. We have the effectivity factor, ability to accomplish the intended outcome, and so we see that once again showing up several times in this equation. And then we have the elegance value. And so thus we have the language, tool, and method each have their own contributions to this equation. And so you have that listed here that you can see that equation. Once the tool and languages are selected, those terms are effectively constant. So a modeler is only able to directly influence the method-related factors here, and therefore productivity, effectivity, and elegance depend heavily upon the methods used to construct the descriptive system model. Every model element has a cost associated with its elicitation, creation, definition, and maintenance. Therefore, if a system can be described rigorously and completely with n elements, each n+1, where I is greater than 0, elements add no value and only increases the cost. Therefore, organizations must carefully construct their modeling methods and style guides to ensure their modeling efforts result in efficiency, effective and well-organized models that support the development of the system of interest. So I know that's gets a little bit technical, but there is a fair amount of research that's has gone on and continues to go on in terms of system engineering and how to optimize it or look at it from various points of view. Well, let's finish up with 2 other topics on this area. First of all, model-based system engineering adoption. Many stakeholders and engineers may find it difficult to separate the information about a system from the means used to present it. If they have a document-centric or diagram-centric mindset, presenting them with a model-driven work products may result in culture shock. It's important for any MBSE effort to focus on outcomes and show stakeholders that relevant information may be presented in different forms while retaining its relevance and rigor. For example, instead of using a large format diagram to show connectivity between components, a model-generated table can present the same information in a formal, amenable to filtering, sorting, and other manipulation. A model-generated matrix can also be used to compactly present the interface and connections. Although the large format diagram may have advantages in allowing a quick overview of the system topology, if it interferes, it is inferior in allowing error-free analysis of connections. Another challenge facing MBSE effort is the learning curve associated with modeling tools and languages. By having subject matter experts own model content and have a team of modelers who own the transformation of that content into the model, teams can lower the barrier to modeling success. Subject matter experts tend to accept system modeling transformations more readily. If they are expected to contribute to the model and consume model products, but are not expected to master all the complexities of the modeling language and tools. Arguably, the most important skill for modelers is the ability to listen effectively. This allows them to grasp key concepts from subject matter experts, construct the model, and create model-derived work products that support analysis and other engineering tasks. It is particularly important that a modeling effort develops early demonstrations of the value, such as an error checking or increasing fidelity of team communications and information representations. For example, absorbing a separate hazard analysis database into a system model and demonstrating the traceability between functions, hazardous outcomes, and mitigation strategies ensures synchronization between the analysis and the architecture. Reliability analysis can also be easily integrated into a system model with relatively straightforward parametric analysis, automatically calculating cost and reserves from allocated and actual values is also of immediate demonstrable value. Many organizations use spreadsheets to calculate this information. This can lead to undetected analysis failures due to formula errors. Models avoid this by applying parametric uniformity to appropriate model elements. System modelers can seek information such as these to reduce non-modeler workloads, improve information fidelity, and reduce redundancy. This helps to reduce friction and resistance to change within the development effort. Although INCOSE's vision is that eventually MBSE will be a standard way of executing system engineering, in the near term it may not be appropriate for all projects. Project management should consider the nature of a product, the team's culture, and the availability of modelers when determining if MBSE is suitable for the project. And finally, in terms of modeling craftsmanship, effective modeling requires a new set of proficiencies that must be integrated into traditional system engineering skills. It is important for the modeler to think like a system engineer maintaining a holistic view of the system as well as understanding the modeling language, tools, and methods. It is also important to view the model as an integrated construct and not just a collection of diagrams and work products. Learning and networking from more skilled modelers are an important part of developing modeling skills. Experts can explain and demonstrate best practices that would take novices significant time and effort to discover on their own. System modeling is still a new field and is important to stay abreast of advancements in techniques and approaches. Dedicated modelers on the system team may be required to manage large models and enforce guidelines for completeness, compliance, and reusability. Well, next, we'll talk about MBSE languages. The most widely used model-based system engineering language is SysML, the system modeling language. It has been developed by OMG in partnership with Nkosi. Its strengths are its usefulness at multiple levels of abstraction, from high-level concept modeling to extreme detail required to model pinouts in a physical architecture, customizability, and significant tool vendor support, both open source and commercial, with noteworthy products from Dassault Systems, IBM, PTC, and others. It is a collaborative standard stewarded by a thriving worldwide community of expert modelers, system scientists, ontologists, and tool vendors. Detailed discussions of the language is outside the scope of this book. Interested students are directed to the SysML Distilled Delegati from 2013, and also there's a practical guide to SysML, the system language modeling language by Friedenthal, Moore, and Steiner. And there's a third edition. The textbook quotes the version from 2014. So those are some references we will also touch in our class. It is in a high-level architectural framework. If a high-level architectural framework is needed, the UAF is recommended because it's based on UML and SysML. This compatibility allows a single tool to be used to model a system at the enterprise level with the ability to expand it with relevant UML and SysML constructs as needed. There are several other possibly, quote, simpler modeling language that have been proposed as alternatives to SysML. These tend to have limited utility and lack support with the broader system modeling community. Modeling of complicated and complex systems requires a precise, customizable, and non-simple language. It is impossible to model complicated and complex systems without a language of suitable complexity. SysML 2.0 is adding significant features to resolve problems and limitations that had suffered over the past decade of use of the 1.x version of the language in multiple domains. Next, we'll talk about model-based system engineering tools. Some advantages of using MBSE tools include the inherent configuration control, usually achieved through a server that enables multi-user collaboration. MBSE tools automatically make changes to the other parts of the system model when one part is changed, /updated, /modified, /deleted, which eliminates the workload of manually examining every diagram, table, and matrix in the system model to implement the changes. Models can be transferred between organizations working on the same project and can be aggregated. This is a value of the development of a complex system by multiple vendors. Aggregation and connections ensure interface consistency. Validation tools, verifying user-specific modeling rules, and built-in error checking, for example, prohibiting the connection of incompatible ports, serve to provide immediate model quality checks. Competent users of the tools provide increased in fidelity and rigor at nearly zero cost and at the same tempo of the development effort. This eliminates need for some types of reviews and contributes to the overall efficiency of the development effort. System engineers must work to ensure that the model is trustworthy, with each element, attribute, and relationship deliberately created in accordance with sound system engineering practices. This allows the queries and analyses based on the model to be trusted. The increased capability of system modeling tools obviates the need for dedicated requirement management tools, version control, connection to architectural elements and source documents, and document generations are all possible with model tool chains. Elimination of requirements management tools eliminates the need for synchronized multiple tools and reduces the cost of the system engineering effort. For example, many modeling tools allow the embedding of element names into requirement text. This automatically updates the requirement if the element name changes, eliminating the need to adjudicate such a change in a requirements change control meeting. In terms of model-based system engineering adoption challenges, when an MBSE effort is initiated, infrastructure and personnel costs must be identified, and stakeholders must be willing to bear them to reap the manifold benefits of adopting model-based system engineering. Experience with previous failed MBSE attempts can also create barriers to the transformation. Other challenges may include convincing stakeholders that MBSE can provide the same, if not additional, insight into utility into their problems in design space. Transformation may require the involvement of partnering organizations and subcontractors working on the design, integration, testing, and operation phase to fully realize the benefit. Once the initial shift to an MBSE approach is complete, there may be additional updates to the MBSE software. These upgrades often result in ongoing licensing costs, as well as a need for architects and modelers to maintain tool proficiency as their duties and positions change. Should be noted that because MBSE is still in the stage of relative infancy, the feature improvements and bug fixes typically included in tool updates make them compelling enough to warrant the effort and cost. Other stakeholders have many different tool preferences, so the system modeler and system architects must be willing to learn each tool and foster interoperability and compatibility. So in terms of common model-based system engineering tool attributes, the system engineering and modeler community continues to grow in parallel with MBSE tools. Some vendors have evolved their products to include a growing ecosystem of federated tools to reach a greater audience. Cloud-based tools do not rely on a specific computer operating system are also becoming more popular. There are also hybrid solutions in which heavy client applications are used by the primary system modelers, but most stakeholders interact with and even selectively edit the model using web-based interfaces. Other key features commonly available are embedded tutorials to show novice architects how to develop artifacts, support them for further use, or how to integrate them with other tools and work products. Other user communities also have formed to showcase the use of tools, and numerous companies hold annual conferences to highlight the best practices of users and previews of further product updates. Academia enjoys a unique relationship with some of the MBSE companies who offer special pricing or discounts to enable a time or compatibility limited version of the tools in order to enable students access to these tools and learn system engineering as well as artifacts development during their courses. They also typically support researchers exploring a novel application of MBSE tools and analysis. Most tools also offer the ability to export data in tabular form, ready for analysis in a spreadsheet or XML files. Many also offer support for representational state transfers, application program interfaces, APIs, and other data interchange formats such as open services for lifecycle collaboration. To support the long-term DoD digital engineering vision, tools exist to exchange information rather than complete files or databases. The fruit of these interoperability efforts will be ongoing improvements in usability and data quality for everyday engineering tasks. Well, next we'll talk about model-based system engineering used in the system engineering lifecycle. And after we complete this short section, we'll get into some examples and we'll see a variety of different model-based system engineering diagrams. So MBSE is used in the system lifecycle. So system models can be used throughout the lifecycle of a system. In the earliest phases of a project, a descriptive system model can be used to capture capabilities, objectives, and the overall system content. The MCOSI model-based concept development working group is developing best practices and methods to maximize the value and downstream usefulness of models created in this phase of the system lifecycle. Typical modeling efforts during this phase include use case and user stories, capture and analysis, the identification of the elements in the system context and their interfaces, and the development of the initial architecture and requirements. Quality checks that enforce documentation of elements and traceability improve the fidelity of the model as these expose gaps. Following the system engineering process, once the architecture is developed and parametric relationships are identified, automated trait studies, requirements, compliance, and derived work products are developed using the model. As it continues to grow, relevant details are added, requirements are created, and verification methods are identified. It is essential that the system model be tested and verifiable. Sections of the model can be shared with other program partners for further development. The master integration model federates these submodels and ensures interface integrity, access rights, security, and intellectual property protections are required with distributed modeling. Once the architecture is developed and parametric relationships are identified, automatic trait studies, requirements, compliance, and derived work products are developed using the model. As it continues to grow organically, relevant details are added, requirements are created, and verification methods are identified. The system model is synchronized with PLM/PLE solutions. That is synchronizing the product structures and properties and other tools such as Ch10a to provide developers with task and associated information. Sections of the model can be shared with vendors or other development partners for further development. The master integration model federates these submodels and ensures interface integrity. Access rights, security, and intellectual property protections are concerns that are being addressed as tool vendors and practitioners gain experience with distributed modeling. Many tools are compliant with the standards such as the Automobile Open System Architecture, AUTOSAR, and Functional Mockup Interface, FMI. These facilitate data interchange and co-simulation in ways never previously possible. It is likely that entirely new methods to derive additional value from these models will emerge with this edition. It will emerge while this edition is in print. Test architectures can be modeled in parallel with requirements development to ensure that test procedures are well defined. The test infrastructure is understood with the same rigor as the system of interest, and what clearly defines a compliant verdict for each requirement. This also enables impact analysis. For example, if the test fails, what requirements, functions, and capabilities are at risk, and efficiency gains, for example, using information about instrument personnel or resource requirements to inform development and test scheduling. Synchronization of test results with requirements in the model also allow authoritative generation of requirement compliance matrices and reports. In operations and maintenance, system models can provide authoritative information about requirements, test results, interfaces, properties, and other aspects of the architecture. Instead of having to sift through entire requirements documents or other information sources, users will be presented with relevant content directly related to their concern. Tool vendors and standard bodies are developing ways to exchange atomic information rather than entire models/files to respond to queries of this sort. End users will be able to consume this data without needing knowledge of the system model or its language. Information will be presented to them in relevant, comfortable formats. Finally, system models will facilitate retirement and disposal of systems, identification of components with hazardous material, those that require secure disposal, for example, contains classified or protected information, or any other necessary criteria can be completed by querying and analyzing the architecture. Failure and warranty analysis can be conducted with an entire life cycle of information to identify new design rules and guidelines for future products. At the end of the product's life, its model and related information can be archived for later reference. This will require some effort to ensure documentation and instruction for later assessment and reuse are provided.